Welcome to The Signal, the podcast companion to the only intelligence report in men's health and fitness that tells you what to watch, what to ignore, and why. I'm Andy Feltovich, founder and CEO. Every episode, we go deeper than the newsletter. Longer conversations, harder questions, and the stories behind the data. We don't do bro science, we don't do wellness theater, and we question everything except questioning. Every dogma on trial, guilty until proven innocent. If you're new here, The Signal is produced by Andy Feltovich, the flagship company of the Collegium of Order and Flow. Subscribe to the newsletter at the-signal.us. Don't forget the hyphen. And if this episode is worth 5 stars to you, leave a review. It's the single best thing that you can do to help us cut through the noise. Now let's get into it. Today we have Dr. Carlene Starck, protein biochemist, metabolic nutrition scientist, and founder of Starck Science, where she translates cutting-edge nutrition science into real-world tools and strategies for consumers, health professionals, and food companies. This is for informational purposes only and should not be interpreted as medical or nutritional advice. Carlene, welcome. It's a great privilege to have you today.
Thank you so much. I'm actually really excited to be here and looking forward to it. So
let's start at the beginning, because I always think the origin story is important, where the real interview lives. So you've got a background that doesn't follow the standard career arc, PhD, structural biochemistry, postdoc, Children's Hospital, working with prion proteins. So if you could just walk us through your Batman, Batwoman origin story, as it were, and tell us how you got to where you are today.
So yeah, it's not the normal trajectory. I mean, most academics, they do their PhD, they stay on for a bit, do a postdoc, go somewhere else, do another postdoc, end up working in the same area, coming on associate professor sort of thing. So I've never really done things in a normal manner in my life, but there is one sort of, I guess, common theme that threads throughout everything. And the big one is just a love for protein and a love for protein biochemistry. And so that really started in my undergraduate years. So I went to uni because I originally wanted to be a vet. I love horses, love animals, that sort of thing. And I thought being an equine vet would be super cool, until I realized one day working on a farm that I was kind of more interested in what was going on inside the animal than actually helping the animal to survive, which sounds a little bit morbid, but it was kind of a key realization. So I ditched the vet thing, but I stayed in science. And so it was my second. Are you getting feedback?
Not on my end. It sounds clean, and we'll filter. We can edit out any sound issues, so I don't think it's a problem.
That's good, just to make sure you're not getting it. So second semester of my first year at uni, I had the best biochemistry lecturer in the world. His name was Stan Moore. He's now at the University of Saskatchewan in Canada, so just in case he's listening, Stan, you're awesome. But he really instilled for me a real love for protein biochemistry. I'm not really interested in carbohydrate, not really interested in fat, but he really sort of instilled that. He had a great love for it and passion. I think that went on, and primarily protein structure. And so then I did my PhD in protein structure, looking at a protein called myostatin, which is actually a really important protein when it comes to muscle growth. So it sort of acts as a bit of a brake for muscle growth. And so the thought was at the time that if we could work out what the structure of myostatin is, we can work out how to inhibit myostatin and therefore allow muscle growth to, ensue, especially in people with, say, muscular dystrophy. So that was sort of the whole thought behind it. And then that PhD didn't go according to plan. The structure of myostatin is extremely complicated, and so I was not successful in doing that. But along the way, it sort of serendipitously went in. I found out that myostatin could actually misfold into this amyloid-like structure. So for those who don't know, amyloid protein is a key protein implicated in Alzheimer's disease. And it seems to, it sort of has a normal structure and a normal function in the body, but for some reason it unfolds and then refolds into the sort of this aggregated form that eventually forms long fibrils. And these are the things which are found aggregated as plaques in the brain of people with Alzheimer's disease. So I found that myostatin could do the same thing, and that sort of led me down the prion route. But I think, and then over time, obviously, I suppose I should finish that story, led me down the prion route. When I was in Canada, so I was doing my postdoc in Canada, I got very heavily into mountain biking and competitive mountain biking and became an endurance athlete in that sport. And I sort of realised that what I really wanted to do is take my research, instead of sort of circling around in lab and academia, and apply it in the real world, especially apply it to exercise physiology, athletic performance, that sort of thing. And when I came back to New Zealand, I got a position at Massey University working in an exercise physiology lab, and so sort of more focusing on that. It was a really tough economic time when I came back to New Zealand, so it was a mixture between just doing, like, following what I wanted to do. I actually marched up to the head of the exercise physiology department and said, "I'm really awesome, you should give me a job." And he was like, "Oh, okay, well, since you think you're awesome, maybe you are awesome, and I'll find some money for you somewhere." I think there's a saying which is, sometimes detours in life take you to the best destinations, or something like that. And my life has very much been that kind of path. Another one of my very good, one of the good influences in my life over time was the head of department when I was doing my PhD. His name was Jeremy Hyams, and he actually said to me, "Carlene, sometimes the best career decisions you make are the ones that you don't plan." And so I sort of held on to that, I think. But anyway, I came back to New Zealand. I was doing exercise physiology. The money ran out. I didn't know what to do. And so I had put my CV into a whole bunch of different institutes saying, look, I'm open for work. And Professor Paul Moen contacted me and said, "I think you'd be really, really awesome for a project coming up that I've got. And it's mathematical modelling." And I was like, "I have absolutely no idea what mathematical modelling is. I don't know how to do that." And he said, "That's okay. I think you'll learn." So like, okay. So I jumped into that, and that pretty much took me to the rest of where I am now. So a focus on protein and a focus on nutrition. I was never really that interested in nutrition before, apart from nutrition that's going to, support my athletic performance. I had some pretty stuffed up ideas about nutrition, to be honest. I was very much, at the time, I think I was trying to follow the keto diet because that's what I'd heard was really good. So I was along the similar lines, but to what I'm doing now. But anyway, I started this postdoc with Paul Moen, and that sort of led into this massive focus on protein and amino acid metabolism, where it really felt quite serendipitous. And then I started with protein, and now I was back working in protein, but in a different way. And so to tie all this together, what I'm really focused on now is amino acid requirements. And the reason why that's important is actually because of protein structure. So it does fit together. Why does that matter? So if we think about protein structure, one of the most fundamental things you learn in undergraduate biochemistry is that every protein has a structure, and that structure is essential for its function. Protein cannot work properly without its three-dimensional structure in a specific way. So if you think about, for example, hemoglobin, right? There's 4 hemoglobin molecules that come together, and they have to hold an iron ION in their center, so that can bind to oxygen, so that can be carried around the body. So and that's a three-dimensional structure. If they don't fold properly, they can't come together, they can't hold on to the iron, and they can't bind oxygen.
Yeah.
So we don't have any oxygen. Anyway, but effectively that three-dimensional structure is predicted by its amino acid sequence. So there's 20 different amino acids, And each structure has a unique composition and sequence of amino acids that have to come together in the right way to make that structure. So if we take a step back and we think, well, what do we actually need to eat? We need to eat protein because we need to get amino acids. There's a specific amount of each essential amino acid that we need that is going to allow every single protein.
So, Carlene, sorry to interrupt you, but now we are starting to get a bunch of feedback. It is recent, so whatever you're doing, so something changed. Not sure if we have any options, microphones, headphones, etc., to prevent that feedback.
I don't have any way of doing that. Would it help if I got headphones? It'll take me a little while.
A little while meaning?
I need to connect them to my.
Actually, yeah, that's fine. If you if you don't mind, and shame on me, I should have mentioned that earlier. That always makes a difference.
Hopefully it'll work. I just need to figure out where my Bluetooth is. I never ever use these, so.
Sure, understood. Yeah, because a lot of people are going to benefit from this message, and we want to make sure.
I'm babbling a little bit, but okay, connect to discoverable, add device, Bluetooth. Oh, actually, I think that's going to be difficult because I need to do it in a different way. What's the best thing to do? Are we still getting feedback now?
It appears to be resolved, at least for the moment.
Shall we? Just because I'm going to need to, it's going to take longer because I forgot that these AirPods
Okay.
are tricky and I need the case and I'll probably need to look up how to do it because that's.
Okay, well, we can drive on for the moment, and hopefully we'll be able to edit it out in post-production. All right.
Do you want me to go back to anything?
So we can truck on. So I was just gonna say that kind of wrap up this section. Say great points on protein quality, and we're gonna come back to that and probably add in some comments about three-dimensional structure. So I'll go ahead and lead in with that, and I'll just have my editor start here.
Sorry about that.
Yeah, no worries. Well, thank you, Carlene, for that excellent summary of your background, and I'm glad you pointed out the importance of three-dimensional structure. We often forget that we're three-dimensional creatures that live in a three-dimensional world. I remember the thalidomide, the issues with that, and was caused by of course, the optical isomer issue, that it was just because it's the same compound, how it's arranged in space makes a difference. So we're going to come back to protein structure, spend a lot of time on that. But I want to go back to your mentors and the training you've had, because I've always stressed the importance that to be the best, you have to train with the best, train under the best, and you certainly did that, working with several of the giants of protein metabolism. So please talk about those mentors that you studied with, studied under, and how that shaped you.
Yeah, I love what you say about if you want to be the best, you have to train with the best, because that's also the story that happened when I was mountain biking, and I attribute my mountain biking success to that specific thing. I was riding with World Cup riders and things like that, and so it just completely changes the way that you think about things and what's possible. And Paul Moen was actually, I had no idea who he was, and so when I started working with him, it was quite a big sort of shock to the system. And then he said to me, probably in my first couple of weeks of my postdoc, oh look, I've got this really good colleague, he's coming over, I think you'd really get on with him, I'd love if you could sit down and have a chat because we're going to do some work together. And this was Robert Wolfe, who is, as you say, sort of one of the giants of protein metabolism. Again, I had no idea who this person was. So he comes over and sit down and have this fantastic conversation with Bob about all things protein. Learned probably 3 or 4 years of study in an hour conversation. And he was also heading off to the gym after our conversation, which was quite cool. But I think the biggest thing was that Paul really changed how I think. He changed the way that I think about science, about how much detail you need to go into in order to fully understand the science. Paul has a very, goes right into the detail, picks everything apart. If we want to understand something, we need to know every single little thing about it, which is kind of that mathematical modelling approach. Bob, on the other hand, is more in the physiological sort of output. He's gotten a huge amount of knowledge and was actually one of the founders of the isotope tracer methodology, which very much is at the molecular level. But we're more interested in, if we put these inputs in, what is the overall response? And so what that did is it gave me a really good understanding about what happens when we eat protein, gets digested, what happens in the body, and then what that physiological response is. So I think it gave me a really, really well-rounded understanding of all of that. And so it's quite good because now I'm sort of Bob's semi-retired. I don't know if anybody ever retires. Paul's semi-retired. And now I'm doing collaborative work with Dr. David Church, who is the sort of successor of Paul. So we're trying to keep that relationship and that output going. I don't think we'll be, big shoes to fill. I'm not sure we'll be able to fill them completely, but
have faith in yourself. So Dr. Church, Dr. David Church, for those of you who don't know, another emerging giant in the field, along with you, Carlene. So don't be modest. You're going to. We fully trust you to carry the torch. And speaking about the importance of good training, I think a lot of your success has also been due to your training in fundamentals, so molecular biochemistry, and that's something like, especially me coming in as an outsider, I'm a diligent study, but I just don't have that training in blocking and tackling fundamentals. So, and you mentioned you mentioned the important how Dr. Wolfe likes to know that every electron, proton, neutron, subatomic particle is accounted for. So tell us about the importance of that training in basic sciences and how that helped you in your career.
Yeah, I agree. I think that is really important. One of the things, I think there's a real disconnect. And actually, I think I can bring in another level as well. So there's a disconnect between, let's say we're talking to dietitians or nutritionists. They're like, eat these foods, get this response. Awesome. Calories in versus calories out. Focus on macros, that sort of thing. Whereas the molecular biology asks, okay, but what's actually happening in the body to create that response? And not so much even what's happening at the sort of blood marker level or tissue level, but what's actually happening in the cells. Because if we can understand that, then we can understand the bigger picture. The other part of it is, of course, having that awareness. I think one of the things that I've always found with biochemistry, and I used to tutor a lot of students coming through, and there was a really clear picture between those people who did well at biochemistry and those people who didn't. And it's the ability to think in the grey area. So a lot of people are very black and white. Have a protein, have this outcome. Have 2 proteins. People have this kind of perception that I've got 2 proteins, they're in the body, they come together, they do a thing. Whereas actually what happens is you've got a massive globular mess of liquid and all these molecules going around it, and 2 proteins that may interact. For some reason, they just get close enough, and then there's enough of an attractive force that they might, attract long enough for a second for that reaction to occur. It's very random and yet extremely elegant. And so when you start to understand that nuance that's actually happening in the body, it gives you an appreciation of the nuance that actually happens in the diet and the context. And so I think that's that missing piece is the stuff that happens in the middle, how we get from input to output. The other thing is, of course, is it extends to what we're doing in our research and the findings that we get in our research. How does that actually apply in the real world? There's that disconnect as well, because that's not the same. A randomized control trial is highly controlled, and we can start to establish a causal effect from a randomized control trial. We know that if we apply this intervention or this much protein, we get this outcome. But at the same time, that's still in a controlled setting. So how does that work in the real world? Which is another layer of nuance and context. So I just think that that molecular biology understanding allows you to hold a massive amount of complexity and uncertainty and chaos in your mind at the same time, whilst still allowing there to be some things that we can measure.
Yeah, that's a fascinating point. It reminds me of my introductory thermodynamics class when they said there's nothing theoretically to prevent all the molecules in the room from coalescing in one corner of the room and starving us of oxygen. But yeah, it's just although it's random and chaotic, by the miracle of statistics, we can channel the chaos into sensible conclusions. So you mentioned understanding the life of the amino acid. Let's walk us through that, because everybody just talks about digestion and absorption, and the story stops there. But there's a lot that goes on in the life of an amino acid. So walk us through that.
Yeah, so there's in the recent paper that we published earlier this year, there's quite a good figure in there sort of talking about that, although it may not be that interesting of a figure to the general population. But effectively, I think a lot of people think, I'm going to eat this protein, the protein's going to get digested into amino acids, they're going to go into my bloodstream, then they're going to go to the muscle, and I'm going to build muscle. Whereas in reality, what you have is I'm going to eat this protein, it's going to get digested into amino acids. Depending on the composition of that protein, some of those amino acids might not make it to the body. The amino acids that make it to the body then have to kind of get through this, rite of passage, which is the splanchnic area, which is also referred to as first pass metabolism. So it's the gut and the liver, these organs that have massive requirements for protein and energy, and they kind of get first dibs at those amino acids. And so there's a bit of a loss that happens here, and based on the best data that we have available, that's kind of on average around 30% of the amino acids that are digested and absorbed into the body. About 30% of those, probably more by the time we account for protein synthesis, but about 30% of those will be lost. It's not really a loss because the body needs them and it uses them, but 30% are not going to make it through into the sort of peripheral metabolism, into the bloodstream that's going to take them to the different areas of the body, including the muscle. So that's kind of quite a big loss. Once it gets to the muscle, of course, then it can enter protein turnover. And protein turnover is this constant cycle of breaking down protein and then building it back up, and then breaking it down and then building it back up, and then breaking it down, and it just goes around and around and around. Now, this isn't just happening in the muscle, it's happening over the entire body all of the time. You've got thousands, tens of thousands, hundreds of thousands of different proteins in the body, and each one of those has a different rate of turnover. So they're all working at different rates, but it's constantly happening all the time. And so most, as I said, most people think about muscle, so we can focus on that. The dietary amino acids that make it into the muscle, they want to get pulled into protein turnover so they can help keep that thing going and amp up the rate of protein synthesis. And so when we're looking at research and we're talking about the ability of a protein to have an anabolic response, that's what we're talking about. How well can it sort of boost that rate of muscle protein synthesis? But of course, this is happening all over the body as well. So some studies that we look at might measure whole body protein synthesis, which is the response of the entire body. But then we have lots of other roles for an amino acid. So that's sort of the major role. Those two things that I talked about, the protein turnover and then the sort of losses that happen in the first pass metabolism. Those are kind of two major roles. Then we have roles in things like neurotransmitter synthesis. So your neurotransmitter serotonin, which is the one that people attribute to mood, precursor to that is actually tryptophan, which is an essential amino acid. And your neurotransmitter dopamine, which most people should be very familiar with now, the precursor to that is tyrosine, which is not an essential amino acid, but it relies on an essential amino acid to make sure we've got enough. So these are just two examples of really important functions. The other thing that is important to note is that the gut has a huge requirement for amino acids because it's highly active. It's turning over at a very rapid rate. And we also have quite a significant loss of amino acids into the gut because the gut's constantly pumping enzymes, shedding tissue, turning over very quickly. And a lot of those amino acids, they never get reincorporated. They kind of move through. They might go to the gut bacteria and then they'll get excreted. So we've got huge amounts of role for all the different amino acids in the body that we need to think about. We can't just think about muscle. We need to think about all the different roles. Other things are hair, skin, nails, menstrual fluid, semen, just if I'm allowed to say those words.
Absolutely, bring it on.
Yeah, but
I might get more viewers that way, so yeah, please.
Yeah, all of the different roles in the body. I think it's fair to say that pretty much every single process in the body relies on protein.
Let's dig into muscle for a second, just because, as you know, it's a subject near and dear to my heart. Everyone talks about local muscle protein synthesis. So there's the kind of the four quadrant model. There's local muscle specific anabolism and catabolism. Those are the first two quadrants. And then there's whole body anabolism and catabolism, the second two quadrants. And everybody loves muscle anabolism, and you've probably seen me rant about this on social media because it's easy to do, right? You have somebody do an exercise, usually a leg extension, because the vastus lateralis is the easiest muscle to biopsy, and then voila, you've got a boring paper that exercise and protein stimulates muscle protein synthesis in the vastus.
To that boring word.
Okay, it's exciting, but after you see 1,000 of the same goddamn paper, it gets a little annoying. So this is going back to our theme of transitioning from the molecule to the RCT, the randomized control trial, to the real world. So in the real world, how do we know that we're doing everything that we need to be doing? Local anabolism in the muscle, global anabolism, local catabolism, global catabolism.
Yeah, so I think it's worth saying that muscle protein synthesis does seem to correlate really well with whole body protein synthesis. So if you're reading a paper and you're seeing that there's an increase in muscle protein synthesis, you can be pretty sure that there's an increase in whole body protein synthesis as well. But in terms of what we actually need to do, I mean, I think this is where, if we go back to that, what we're talking about with having a requirement for essential amino acids, this is where we really need to have an understanding of how much do we actually need to be consuming in order to hit all of those different requirements, as well as making sure we're getting in enough energy. So if we're wanting to do the right thing, if we're wanting to grow muscle, if we're wanting to make sure we've got enough protein to supply the amino acids for all of the body, we need to be consuming enough protein in the first place. We also need to be considering the context. So are we consuming enough for who we are, for what our goals are, and how old we are, for all of that sort of thing. And then we need to apply a stressor, such as resistance training, in order to really optimize that anabolism, as you said. I think one of the things we were talking about, catabolism. So catabolism is the breaking down, anabolism is the building up. And I think we need to make sure that we recognize that catabolism is really important. is just as important. The reason being is that there's a reason why the body breaks down protein and builds it up and breaks it down and builds it up. Part of that reason is that during sleep, we need to be supplying amino acids to the body for all of their different roles. And the greatest supply of those amino acids is the muscle. Muscle is sort of the greatest reservoir of amino acids. It's not a storage facility for amino acids, but it is a reservoir. So we need those amino acids to be broken down. And then we need to eat protein to supply amino acids the next day to build that back up. But that breaking down also has a role in maintaining the integrity of the different proteins we have in the body. And sort of that goes back to my PhD work and my first postdoc about protein misfolding. So proteins are misfolding all the time. The ability of a protein to fold into its three-dimensional structure relies on a number of different things, the right environment, and mistakes happen all the time. I mean, we're human, right? So mistakes are happening, and we have processes in the body that sense those mistakes, and will, like, for example, there's a little alert that goes off, hey, we've got a misfolded protein. We are going to break that up and chop that down and get rid of it. So that's part of that integrity. If we didn't have catabolism, we didn't have protein breakdown, we would have a greater proportion, this is just one example, a greater proportion of misfolded proteins. And those misfolded proteins, A, can't do their proper job correctly, but B, have the ability to wreak havoc in the body. So catabolism is important. And I think this then touches on that exercise thing as well. This is why resistance training is such a powerful tool for overall health. Resistance training increases the rate of both breakdown and synthesis. So we're constantly remodeling our muscle, remodeling our protein all over the body, maintaining its integrity and its health. And I think this is, Gabriel Lyons, I think, talks about this quite a bit, the difference between muscle mass and muscle health, or muscle strength and muscle health. You know, you can have a lot of muscle, but it might not be healthy muscle.
That's an important point. It's not about the net amount of muscle, it's also about the quality, and it sounds like by undergoing resistance training, you're not only increasing the net amount, but also you're constantly remodeling and taking out the trash, as it were. Exactly. I want to get into protein quality. It's something that you really opened my eyes on. I kind of went overboard with just carpet bombing. If you get enough protein, then if you just eat a lot of protein and get enough of it, then all these other considerations drop off, including quality, which I still think is true to some extent. But you really changed my mind about quality and why quality matters. So please walk us through how you define protein quality and why it matters.
Yeah, so protein quality is quite a big conversation. I agree. It's very important. So when we talk about protein quality, what we're talking about is how well does one protein, an individual protein, supply all of the essential amino acids that the body needs at their required amounts after accounting for digestive losses. So what this means is we eat protein, as I said, not all protein is going to make it into the body. We will have some digestive losses. Of those proteins that make it into the body, what is the composition of that protein in terms of its essential amino acids compared to what we know, what have been provided as requirement estimates for each one of those essential amino acids. So the thing about protein quality, so it's got a few limitations. So the pros are it allows us to directly compare different proteins for their amino acid composition after accounting for digestive losses. The cons are nobody eats only one type of protein in their diet. So when we think about protein quality, we're saying how well does a protein supply everything if we were to consume it at the estimated average requirement for protein. If we were to consume what they tell us to consume, how well is the protein doing its job? So we can compare, but yeah, as I said, we don't only consume one type of protein. So then we have to consider how do different proteins interact? How do different proteins interact with the other components in our food that we eat, carbohydrate, fat, fiber? Then we have to say, okay, amino acids are entering the body. That's our protein quality. But what happens in all of those other processes we talked about? What happens during first pass metabolism? How much actually makes it to the body? How well does a protein actually stimulate muscle protein synthesis? Just because an essential amino acid composition is getting through the digestive system, that doesn't necessarily mean that the same composition is ending up on the other side of our gut and liver. There's lots of other processes to take into account. So I think protein quality is a great start, a great starting point, and it allows us to directly compare different proteins for their potential value in the diet. But it doesn't necessarily tell us the whole story about how that protein is being used for its different roles in the body.
So excellent excellent clarification on some of the myths and some of the limitations of protein quality as it's commonly understood. I want to, and this is my terminology, not yours, but I think you're stuck with it. The Starck factor. So a practical question that practitioners like myself have had is when we are recommending essential amino acid supplementation, that is supplementation with just the essential amino acids as opposed to a whole protein supplement such as whey, how do we factor that into our daily macro targets, our daily protein targets? Because the intuition is that it's more concentrated than a whole protein, so it's probably not a 1-for-1. But then the question is the exact number. So I just based on that paper, the conversion, my first conversion was 2.4 grams of whole protein equals 1 gram of essential amino acids. And then you came back and said, well, external validity, extrapolating, you probably need to throw a buffer in there. So I said, okay, two for one. One gram of whole protein equals 2 grams of essential amino acids. So tell us about the Starck factor and how off base I am.
Well, I mean, it's a good. I don't know how well I can keep that label, but if it's your label, that's fine. But what we're really talking about here is we're talking about how essential amino acids are used in the body. Because what we have to think about is the fact we don't just have essential amino acids, we also have non-essential amino acids. Okay, so when you eat a protein from whole food, protein quality is really focused on essential amino acids because these are the amino acids the body can't make itself. The body has to get them from the diet, otherwise it's not going to be able to build muscle. It's pretty much commonly thought that as long as you're getting in enough essential amino acids, your body can then use those essential amino acids to make all of the other non-essential amino acids that we need. So that's sort of what you're talking about. Is there's some studies that show that as long as we are taking in, if we give some people, just essential amino acids, maybe 10 grams, I think the lowest amount is like 3.6 grams, according to Bob, just essential amino acids, we will get a robust stimulation of protein synthesis. And that's because the body has its own supply of non-essentials, but also if we're missing any non-essentials, the body can convert some essentials into non-essentials. It's a process called transamination. Not all the essential amino acids can do it, but the majority can. In reality, it's not quite that simple because what we're finding out is that some non-essential amino acids may actually be conditionally essential and limiting in certain situations. We also know that the body's really good at sort of making up for any losses. So just because we see a robust stimulation of muscle protein synthesis in the short term, that doesn't mean necessarily that what we're providing is adequate. The body may be pulling amino acids from other areas in order to support that. But if we assume that we've got a healthy person, they're getting in enough protein, all of their processes are working really well, they're not in any sort of extreme conditions, we can say that if someone was to consume just essential amino acids at a high enough amount, it would supply what the body needs. And so this recent paper that you're talking about suggested that in a perfect situation, that ratio of essential amino acids to non-essential amino acids is around 42% to 58%, 41, 59, 42, 58, that sort of thing, which is where you're coming up with that Starck factor number of around 2 to 1. That if you wanted to calculate how much essential amino acids you'd need to actually supply protein, then effectively if you had 2 times the amount of essential amino acids, or if you had just essential amino acids, then it could supply the extra non-essentials that you'd need as long as you consumed enough.
All right. Well, coming back to those non-essential amino acids, and how some of them might be more essential than we initially expected. Tell us about glycine and the role of glutathione production. Everybody's favorite topic right now, glutathione, the so-called mother antioxidant.
Yeah, so glycine is from the modelling that we did. One of the key findings is actually that we have a huge requirement for glycine in the body. We have a huge amount of different. Glycine has a huge amount of different roles. So it's the smallest amino acid, but it's small and mighty, so it does a huge amount of roles. And as you mentioned, it is one of the components of glutathione. So glutathione is actually a tripeptide, which means it contains 3 amino acids, and glycine is one of those. So if we don't have enough glycine, we effectively cannot make enough glutathione. It has been suggested that glycine is the rate-limiting amino acid for glutathione. So glutathione is the master antioxidant. What that means is that it has the ability to help to combat oxidative stress in the body. So oxidation happens all the time. It's really important for function. We need it for signaling. We need it for processes. Every time we exercise, we're generating what we might have heard as free radicals. So sort of oxidants and everything that can go through the body. And the reason why they're so important is because they're highly reactive. And so they can stimulate other reactions. But of course, if we have too many of them, this can become a problem because they are highly reactive. So we need to have some kind of system to keep that balance in check. And glutathione is one of those things that, so when we talk about an antioxidant, that's what it's doing. It's helping to keep that balance. And glutathione is the body's primary way of doing that.
And let's dig into another important function of us. If I understood correctly, some of these non-essential amino acids. You talked about neurotransmitter production. Was that accurate? Some of those non-essential amino acids important?
Yeah, both essential and non-essentials.
Both essential. So one of the things that I've been experimenting with is I started taking essential amino acids. Obviously for muscle growth and recovery. But I also anecdotally, again, sample size of n equals 1, started noticing some increased cognitive performance. Has there been a lot of studies on essential, non-essential amino acid supplementation and cognitive performance?
Well, I'm pretty sure that Dr. Church has some stuff in the works, so that'll be coming out. I mean, there has been some studies. They're not showing anything really solid. So there's been quite a bit of research looking at tryptophan supplementation and also tyrosine supplementation for affecting increased serotonin and dopamine production. The tryptophan research, it's difficult because, of course, in order to have a cognitive effect, we'll eat something that has to make it through the gut, it has to make it through the brain, and then it has to cross the blood-brain barrier in order to affect overall cognitive changes. So that becomes a little bit tricky when we're looking at sort of dietary intake. But these things do happen. Sometimes it's a dose thing. With tryptophan, it's a bigger story because tryptophan has to compete with other amino acids to get into the brain. So that's some of the, I don't know if you've heard some of the things around making sure you have enough carbohydrate. A lot of people will say that you need carbohydrate to produce serotonin. Not quite true, but carbohydrate does help to improve the uptake of tryptophan into the brain. I think there's a little bit better research with tyrosine in supporting dopamine. Dopamine production, and tyrosine is one of the things that can be effective in something like Alzheimer's disease, or there's also a Cushing's disease, which can impact dopamine production. So I definitely, I'm definitely a proponent of taking essential amino acids and even some non-essentials for cognitive performance. The research is emerging, but every single person I've talked to that uses essential amino acids for that purpose will see beneficial effects.
Okay. Well, hopefully so hopefully my theory will be validated. It will do wonders for me and my street cred. I've always joked if you're right enough for long enough, maybe people will start listening to you. But maybe that's also just wishful thinking on my part.
Yeah.
I want to dig in a little bit more to the essential, non-essential, conditionally essential distinction, because a lot of people, and I've fallen in this trap, are under the impression that non-essential or conditionally essential means that we don't need to pay attention to them. But it sounds like that, particularly in the case of glycine, the rate-limiting glutathione precursor, that it's often difficult to people are often deficient or at least suboptimal. So what do you think about supplementing with that, possibly in the form of collagen, as you've mentioned before in our discussions?
Yeah, so I've played around quite a bit with supplementing with pure glycine and with collagen. This is one of the things that I'm sort of tossing up between at the moment is a lot of people take collagen for joint health and say that it improves joint health. There's not a huge amount of research behind that supports that outcome. And if we think about it, when we eat collagen, the body doesn't eat. The digestive system doesn't sort of take the collagen and just absorb it straight away and then it goes to your joints where it's needed, or to your skin. It gets broken down into its constituent amino acids, some peptides, and then it has to go into the body and then get remade. And so what we're doing when we're having collagen, if we're trying to support joint health or skin health or hair or whatever, is that we're supplying the sort of the building blocks that hopefully then will improve overall synthesis. But one of the key amino acids in collagen is glycine. So glycine I think it's around 33% or something like that. I could be wrong. I'm pulling numbers out of somewhere in my brain. But it's a huge proportion of glycine. And so for every sort of 10 grams of collagen you consume, you might get around 3 grams of glycine. So my hypothesis, if you will, is that a key function of collagen is actually to provide the body with glycine, because it is extremely important, not just for glutathione, plays a big role in helping to balance methylation processes in the body. A lot of people have talked about methylation. It's one of the most fundamental pathways in the body. Methylation supports so many different functions, anywhere from DNA synthesis and RNA synthesis through to helping to regulate neurotransmitter production and breakdown. It's also got a huge role to play in cardiovascular health. So the thought is that glycine can also play a big role there. Glycine also seems to have a sort of calming effect in the brain. I'm pretty sure it can bind. There's a neurotransmitter, I think it's GABA, could be wrong, not a neurologist, but does seem to have a calming effect. The other thing which has been proposed for glycine is that having it before sleep can actually enhance sleep. So it seems to decrease core body temperature if you take a large dose, which is a key factor in supporting sleep. So I think there's a lot of different roles. We haven't got enough science to say anything in particular, but it's not going to do you any harm. to supplement with collagen for the purposes of glycine. There is some research showing that in sort of average healthy people, taking additional glycine does improve glutathione synthesis and glutathione status. So I think that's good evidence that you could definitely support your health with it.
Okay. Yeah, I've always been skeptical of the collagen and joint health hypothesis. One, for the reason you mentioned that these collagen, you don't actually eat and absorb collagen, you eat the raw material, and like every other most every other protein, it gets ground down into its constituent parts. But I like your theory about the glycine as all its other beneficial functions beyond glutathione production. I think that's very intriguing. What to we could talk about, especially you could talk about. I'm sure you could talk about protein all day, all week. But I want to get into another trending topic, fiber maxing, and how fiber is the new protein, which is a strange, which is a strange metaphysical possibility, a physical possibility. Two things being different but the same. So if you could walk us through fiber maxing, the new trend, what are we actually looking for with fiber? What are people missing?
So with fiber, the key argument is really, and I think the reason why people are talking about fiber as a new protein is that the key argument is that people aren't protein deficient, but they are fiber deficient. And so if we're going to be focusing on anything in the diet, the fact that, if we look at, say, if we took NHANES dietary intake data, so the US National Nutrition Survey data, and we look at people's protein intake, it comes on average at sort of 1.1 grams per kilogram body weight per day, which is greater than the minimum recommendation of 0.8 as the RDA. Whereas most people with fiber, the recommended intake is around 30 grams per day, depending on your age, your sex, etc. Whereas people are sort of around the 15 grams, about half that amount. So because people are consuming so little fiber, we should be focusing on fiber. The other part of this is, of course, that there's a huge amount of research supporting fiber for health outcomes, cardiovascular disease. So as we increase fiber intake, we see decreased risks for cardiovascular disease, type 2 diabetes, mortality, cancer, all of those things. So we know there's a beneficial relationship between fiber and health. We know that people aren't eating enough. So let's tell people to eat more and more and more and try and improve health. But this is the way that nutrition seems to work in nutrition science. People are like, hey, there's this awesome health outcome. There's this one nutrient that seems to do these things. Let's jump on it. Let's shove it down everyone's throat. The same thing happened with protein. That doesn't mean we should be putting protein into chips and ice cream and everything, right? Like, let's tell people to consume protein in a healthy way, but that's beside the point. I mean, fiber is never going to be the new protein because they have completely different roles in the body. And I have a slightly neurodivergent brain, and when I hear fiber is the new protein, I'm like, it doesn't even make sense. Who came up with that? Like, it's just not scientifically possible. But I can see where they're going at. What they're trying to do is trying to say fiber is the new protein in terms of the new thing that we need to be focusing on and trying to up that. I have some issues with fiber, and I've thought about it quite a bit, wondering whether it's actually as important as what everybody makes it out to be. And this is just my personal musings. It's not based on anything. It's definitely based on the evidence, but the sort of thing that keeps me up at night. Because we have all these people that are on the keto diet and the carnivore diet whose fiber intake is probably, on the carnivore diet, you've pretty much got 0 grams of fiber. On the keto diet, you're probably lucky to hit that 30 grams. And yet, we're not seeing any massive negative effects yet from those diets. There's been a few things come out, unhealthy gut markers and so on, but we're not seeing any really negative health outcomes, and we know that it improves metabolic status quite effectively. And yet, on the other side of the coin, you've got all these, people on highly plant-based diets we see positive effects. And what I'm wondering is, when we're looking at fibre intake in epidemiological research, so we're looking at the entire diet, we're not just looking at fibre, we're looking at everything else that comes with that fibre, primarily bioactive compounds in plants, which also have been shown to have the same effects on health as fibre. Reduce risk of cardiovascular disease, reduce risk of cancer, reduce risk of type 2 diabetes, all of that kind of thing. So I don't know if we can attribute all of the health effects to fibre. What we can attribute really strongly to fibre is digestive health. And there's a lot of, if we look at randomized controlled trials where we are supplying a fibre intervention, it's very, very clear that it supports digestive health. And that would be the big outcome that I would suggest may be impacted by things like the carnivore diet and the keto diet down the track.
So let's talk about digestive health for a moment. What do we even mean by that when we talk about digestive health?
Yes, how well do we poo is what most people go to.
Important.
It is important. I mean, our digestive system starts in our mouth, right? Really, it starts when we consume, goes down our throat, all the way out to our rectum anus when we excrete the stool. But if we think about the digestive system, one of the most important parts of it, yes, we've got the gut microbiome, but I would say that further upstream of that, we've got our gut lining, our mucus layer. And our digestive system is sort of, it is inside us, but it's really external to the body because it's exposed to the outside world. And so that gut lining is kind of a barrier. It's like another skin. It's a barrier between our gut and the rest of our body. And so the integrity of that gut lining is hugely important. And the gut lining is also the thing that houses our gut microbiome. So to maintain that integrity, what we need to do is we need to be, as we talked about with protein turnover, constantly breaking it down and building it up and breaking it down and building it up. And fibre has a role, in soluble fibre mainly, in helping to sort of shear that lining and break it down and pull it off so that then protein can be rebuilt. So that's a big role for fibre. The other part is, of course, we want to make sure that we're moving everything through the body because that helps to maintain a good rate of digestion, absorption of nutrients. The other part of, there seems to be a relationship between fibre intake and colon cancer. And so it does seem to have a role. Again, I think this may be more to do with potentially bioactives, but it does seem to play a role in reducing that risk. And so the health, I think that's really the health of the gut microbiome and supporting that, because the fibre that we cannot digest is a substrate for the gut bacteria to consume, and then they are part of that consumption is they sort of ferment the fibre, and that produces something called short-chain fatty acids, among other things, which seem to have really good roles in the body when they get absorbed. So for me, really, if we're thinking about digestive health, we're thinking about how well does the digestive system actually work in terms of moving things through, but how sort of robust is our gut lining, what is the integrity of it, and how healthy is our gut microbiome?
Yes, I'd never thought of that, the importance of fiber and that turnover, that protein turnover in the lining, some analogous to the remodeling that resistance training does in the muscle. So very, very insightful. Let's talk a little bit about phytonutrients. There was an old joke. Why do people focus so much on macros? Well, it makes for easy math. There's only 3 of them. Then you want to get into the micronutrients. Then you've only got a few dozen. Now we go into phytonutrients, bioactives, polyphenols, and we've got thousands that we know about and probably more we don't know about, many and very few of which we actually understand. So let's spend a moment to just talk about that final frontier. I hate to say final because I'm sure there's going to be another frontier. But let's talk about those bioactives and their importance and what we know about them for a moment.
Yeah, I mean, as you mentioned, there's a huge amount, and there's a lot of people working specifically on them. I think we know the most about the carotenoids, to be honest, which is the sort of yellow, orange, red colours. So this is the thing which always, I get very excited by very basic phenomena, but the colours of fruits and vegetables that we eat. That colour that we're seeing is actually those, a lot of that is coming from those bioactives, because they are a pigment, they're a bioactive pigment. So when we see yellow or orange or red, that's a clear indication that it's got carotenoids. And when I say carotenoids, I'm talking about things like beta carotene, alpha carotene, things like that. And there's quite a bit of research suggesting that there is a beneficial effect of carotenoids on reduced risk of cancer, especially skin cancer, because the carotenes seem to sort of insert themselves into and house themselves in our skin cells and provide protection. Where does that protection come from? A lot of those roles are antioxidant roles. We've already talked about antioxidants, but they seem to have a huge number of other roles: anti-inflammatory, anti-tumour. They seem to help to prevent the growth of cancer cells. One of the big limitations is that most of our research comes from mechanistic studies, so looking at animals and looking in cultured cells. We don't have a huge amount in humans, and part of the reason for that is because we seem to have a difference in effect when we supply phytonutrients in their whole food form versus when we isolate them. So they seem to have this synergistic way of working, which is really nice, but makes it very hard to study. The other interesting thing is some of them have sort of bimodal effects. At low doses, they're really effective, and then at high doses, they can become quite toxic. Because one of the ways they actually work is not necessarily have a direct antioxidant effect, but because they are slightly stressful to the body, they sort of stimulate the body to increase its own antioxidant effect. And then that helps to mop everything up. Whereas if we give the body too much of it, it sort of overwhelms the body's response. So they all work in different ways. The other interesting one is anthocyanins, which are a type of polyphenol. And you'll get those from things like blueberries, blackcurrants. And there's a huge amount of research suggesting that these anthocyanins have a role in recovery, especially muscle recovery from exercise.
So not too little, not too much, and don't try to perfect that which God has already perfected. Just eat the whole food. No, you don't need you don't need a Franken food, functional food. Well, never say never. Everything has its place. Again, we could of course talk for days, but there's one important thing I want to touch on, and this gets to the whole false dichotomy of plants versus animals. One of the implications of your research is that protein quality matters, and then the debate immediately goes to how do you get high quality protein, and slap me if I'm wrong, animal protein is higher quality than plant protein the way we define it. So how do you counter how do you address the false dichotomy, the warring, feuding pagan diet cults of carnivore versus vegan, and what you're actually trying to communicate with protein quality?
Well, that's that black and white thing, right? We can, carnivore versus vegan is a really good example of either it's one way or the other, and it's not. It's those are two ways of eating. I definitely believe that we can obtain what we need in many different ways, but if we look at the science and we take a very objective view, so there's the science and there's what the science shows, or what the data show, and then there's ideology and our beliefs and how the way that we eat can sort of form a big part of our identity. And if we really want to understand things, we have to keep those separate. So if we look at the science, it's very, very clear that animal proteins are higher in quality than plant proteins. And that's not because they're better in a sort of moral way. It's just that the body digests them so much more effectively. And on top of that, the amino acid composition of animal proteins is much more similar to what the body needs, which makes sense. We are animals. So you would think that other animals would have what we need and the amino acid composition that we need versus plants. Plants, or the fiber, they have some anti-nutrients in there that seem to decrease the digestibility of plant protein, so we just get less into the body. And then they have a much lower proportion of essential amino acids in general than animal protein. So those two things together mean that quality is lower. How do I put them together? I'm very much if we look at a team of people working in an organization, a great team has a mixture of strengths. So we might have someone that's really, really ideation, ideas, creation, and going for things. That person is awesome, but they're terrible at follow through and implementation. So we need somebody to come in that's really good at taking those ideas and making them happen and executing. And then we probably need someone that has the ability to audit what comes out and make sure that the quality is high. So we have all these different roles. And that's the way I think about food in the body. Animal proteins are the most effective, efficient, especially when it comes to maintaining a caloric balance, way of supplying the body with protein. Plant foods and plant proteins are great at providing fiber and phytonutrients. So in my mind, put those things together and you have a perfectly balanced diet. That does not mean you can't get what you need from plants, but you have to realize that there's a trade-off. I'm not going to get as much protein or essential amino acids, so I need to eat more, and then that may mean that I need to eat more calories in order to get that protein. So how am I going to balance that out? So I just find that to keep things really simple and outside of whether I'm a vegan or a carnivore or whatever it is, the combination of animal protein, plant foods to support that protein, supports health really, really effectively.
Yeah, you're absolutely right. It's so hard to separate science from identity, and I've grappled with that my entire career, just trying to tell people, look, I do whatever you want, vegan, carnivore, whatever. I'm just trying to objectively communicate what the data say.
Yeah.
Unfortunately, all good things must come to an end, so we're coming up on the lightning round. What's the most overrated nutrition trend you'd like to see go away or at least stop hearing about?
I'm going to get in trouble here, but it would be what we just talked about, which is probably, I don't want to say veganism because I know that there's that belief aspect, but probably the plant-based being the way to go.
Absolutely.
Purely because of the science.
Absolutely. And again, it's worth re-emphasizing, if God outranks me, if you're, even for ethical convictions, if that's what your conscience tells you to do, great. But
Yeah.
when you try to mask it in science, that's when I have a problem. If you could fix one thing about how protein research is communicated to the public, what would it be?
It really is that focus on protein as an amount and communicating the amount of protein, moving into talking more about amino acids. I think that people need to understand that protein, we don't eat protein for protein, we eat protein for the amino acids. What does that actually mean, and how do I obtain those?
All right, and last and final, personal question. What advice would you give to your younger self if you could talk to her?
So it's an interesting question because I actually have talked to given a few talks to young people and given them advice. And the one that I would say to myself, although I think my younger self was already like this, but is to always challenge the status quo. So I think it's very, very easy. I mean, I had some great mentors and researchers and ongoing collaborators. And the reason why they're so great is because we could have conversations where I could challenge them. Sometimes I'm wrong, and they're like, no, this is the reason why. Okay, that's great. But they were always open to that. And I think we always need to learn how to stand back and look at the data, question it for ourselves, investigate, and figure out what works for us, as opposed to constantly just following whatever the latest trend is.
Absolutely. I'm glad you brought that up. You should never always ask the question. Don't assume somebody's thought of it before. And I'm talked a little bit about this offline. Some of the things I'm stumbling on with third-party testing. finding out that just nobody's asked these questions before, and when you start asking questions, you get some pretty frightening answers. So more on that.
Knowledge evolves, right? We can't just we don't sort of learn something and then that's it. If you look at the literature now compared to what it was 20, 30 years ago, some things still hold, some things have completely changed. So,
Absolutely. And before we part ways, the listener who wants to learn more and follow you, I know you're active on LinkedIn. If you're not currently following Dr. Starck, you need to get on it. What else should our listeners be doing?
so one, I've kind of got so many things on the go. I've got a website which is Starck Science, so STARCK science.com. That is currently it's getting updated, but hopefully soon. One of the things that I'm actually doing is I've built a protein quality calculator, which is going to be on that site, so you can go in and play around with your diet and figure out what the protein quality is, and it'll give you a report on that. So I'm excited about that to put that on the website. I am going to be starting a YouTube channel. That's one of my to-dos, but probably the best way to follow me at the moment is LinkedIn.
Great. Well, again, Dr. Starck, it's been a great honor to host you and look forward to hearing more from you.
Thank you so much, Ron. Thank you.